In this lecture, I'll be talking about geologic time, which has a subtitle of 4.5 billion years of fun on Earth, and that is 4 with a 5 followed by 8 zeros. So that's a big number. And so that's one of the quandaries of studying geology and other historical sciences is that we're dealing with long amounts of time, large amounts of time. And so sometimes it's hard to wrap our minds around this, especially when we have difficulty remembering 50 years ago or 100 years ago. So the Earth is very old, and that has allowed it to evolve over time as well as for other processes such as evolution and so forth. So it's a big amount of time, and that's one of the things we have to grapple with. Many people have thought about geologic time and the age of the Earth, and here is a abbreviated list of some of those people that have done work in trying to understand how old the Earth is. Starting with Aristotle, 300 BC, and 1100 years later, Da Vinci in the 1400s, they made observations of marine fossils in mountains and came to the appropriate and correct conclusion that this must have involved a lot of change and therefore must have involved significant amounts of time in order for marine fossils in rocks to be above sea level. And so they made some pretty interesting observations. Another notable person was James Ussher in the 1600s. He was quite a scholar. He did a very detailed study of the Bible and other historical documents to try to document how old the Earth is. And his methods were very thorough and very legitimate. It's just that his data was a little bit biased. But he came to the conclusion that the Earth came into being the night preceding Sunday, October 23rd, 4004 BC, which makes the Earth somewhere around 6,000 years old. Much later, in the 1800s, there were several geologists who worked on this problem. These were people that were making observations of sedimentary rocks in terms of looking for coal, which was being used to fuel the Industrial Revolution. And they made a lot of observations of the correlation between different rock layers. One of the estimates that a geologist made was that based on accumulation of sediments, is that the Earth had to be around 6 million years. So we've moved from thousands of years to millions of years. Many people, however, wanted to make a more quantitative study of how old the Earth was. One of these people is William Thomson, who was later known as Lord Kelvin. He worked in the 1860s on this problem and used a model of the cooling Earth to come up with the age of the Earth. His premise was that the Earth started out as a molten planet, completely liquid, and then cooled over the years to its present state. And based on his calculations, he got numbers between 20 and 100 million years, which is obviously a big range. But the important thing here is we're moving from thousands to millions to 10 or hundreds of millions of years. The next stop on this voyage is the 1900s, where the discovery of radioactivity and the half-life of isotopes brought in the age of radiometric age dating, where rocks could be sampled and analyzed, or minerals from them analyzed, to determine the age of those minerals based on radioactive decay. And this put the age of the Earth at an astounding billions of years, which was quite a shock. But also consistent with lots of observations of both changes in the fossil record as well as documented Earth processes like the raising of mountain belts and erosion. So, in summary, we've moved quite a distance from looking at marine fossils to using very elaborate techniques, and also moving from the age of the Earth being in thousands of years to being in billions of years. So to tell time, we need some type of clock. And here's a nice image of a couple of gentlemen who are painting part of Big Ben, which is a clock in London, a very famous one. And time on Earth based on astronomical phenomena like the orbit of the Earth around the Sun and the movement of the Sun across the sky. And so our standard for time in terms of years is based on a orbital parameter of the Earth revolving around the Sun. But what is the geologic time standard? What are we going to be using as a standard to determine the age of the Earth? Well, fortunately for us, it's things that we have studied, and the things that provide the standard for understanding the age of the Earth are rocks and structures such as faults and folds. And here's just a few examples to illustrate that. Here we have a nice image of the sedimentary rocks and basement rocks in the Grand Canyon. This is a nice record of a large amount of geologic time. Here we have a picture of a fault which cross-cuts sedimentary layering, a basalt which cross-cuts granite, and this very nice metamorphic rock which yields minerals that can be dated to determine the age of the metamorphism. So understanding these rocks and these structures allow us to determine the age of the Earth and the age of different geologic processes. So, moving on, there are two parts to understanding geologic time. The first part are comparing ages, and this part is called relative age dating. Now, in this process, we're only comparing things in terms of whether they're younger and older. And as an analogy, here we have some angry-looking adults and equally angry-looking children, and what we can infer from this relationship, there's Bart Simpson, is that these folks over here are older than these folks. Okay, we might not know how many years they are, but certainly based on their stature and what we know about the Simpsons, here are some kids, they're younger than adults. Now we can do the same thing in geology. Here's some layers of sedimentary rocks. Here is a line that is common to both sides of this fault. And so we know that, or we can infer because this line is cut by the fault, that the fault is younger. So that is a relative age dating process. The fault is younger than the sedimentary layers, and we'll talk about that process in a second. Now the other part of age dating are absolute ages. And absolute ages involve determining the exact or somewhat exact age of a phenomena, a rock, a geologic process. By analogy, we can look at the Simpsons again. Here's Homer eating a donut. During the show, he was 36 years old. And here's Bart, and during the show, he was 10 years old. So the absolute ages, 36 and 10, tell us the true age difference between these two phenomena. Now in geology, we do the same thing. Here is a sequence of rocks, and these have been age dated, and we have a range of numbers 570 to 505 million years for the Cambrian, up to the Pennsylvanian, which is 320 and 260 or 286 million years ago. And the numbers aren't important, but what is important is that you can see these layers have numbers associated with them. It's just not that this layer is older. This layer is older than that layer. And the way we do that is through radiometric dating. This is a plot of isotopes remaining and the number of half-lives, and we'll get into how that is used in a future lecture. So when we combine these, the relative ages and the absolute ages, we're able to construct a geologic time standard in order to understand the age of the Earth and the age of different geologic events. We'll talk about the guiding principles that dictate what I'm about to say, but here are the relative ages. We know that the sandstone here is younger than the basaltic lava flow by a principle called superposition, which we'll talk about in a second. we know that this cuts across these layers and therefore is likely younger. And when we date these, the basaltic lava being 25 million, basaltic dike being 20 million, we know that sandstone is deposited between those two age dates. So we've used a combination of relative ages and absolute ages in order to understand the age of these layers. In the next few slides, we'll be looking at the rules for relative age dating of geologic features. Okay, these rules are also called principles, and they have been built upon hundreds, if not thousands, of observations that have continually been shown to be correct. So the first principle or rule or law is called the principle of superposition. This simply states that the oldest rock layers in a sedimentary sequence, the oldest rock layers are on the bottom and the youngest rock layers are on the top. So this makes sense based on what we observe happening in natural environments. And even when we make cakes, we make a cake, the older layer of the cake goes on the bottom, the younger one's on top. So that's the principle of superposition. The next principle is called the principle of original horizontality. Now, as we saw in the previous slide, layers of sedimentary rocks start their lives out as parallel to the Earth's surface. So, if we come across rocks that are now not parallel, that are at an angle to the surface, here's the Earth's surface, then there must be an event. There must have been an event that caused these rocks to now stand at a very steep angle. And for this case, the event is folding of these rocks, which produces this very nice steep inclination of the sedimentary rock layers. So that's the principle of original horizontality. The next principle is the principle of cross-cutting relationships. And this simply states that features that cut across other features or structures are younger. So here's that sedimentary layering again. Here's the fault which cuts it. This layer is the same as that layer. So this fault has to be younger than the layering. Okay, and where is the oldest layer? Well, it's probably down here somewhere. So this would be the oldest, the youngest at top, the fault next. This is also true of igneous dikes. Here's a granite cut by a basalt, and the basalt must be younger because it slices through this granite. So that's the principle of cross-cutting relationships. The next principle is the principle of inclusions, and there are two parts to this. So what this principle says is that the rocks that are included within another rock must be older. So let's take a look at this outcrop, person for scale. This is granite here. Here are pebbles of granite within the sedimentary rocks. So this granite must have been present before these sedimentary rocks, because these sedimentary rocks accumulated or eroded away at the granite and accumulated some of the fragments of that. Okay, so if we could age date the granite, we would see that the sedimentary rocks must be younger. Okay, so that's one of the principles of inclusion. Here's a variant on that. So here is the same outcrop, but it has a different relationship. Here in the granite, we have inclusions of the sedimentary rock, which have been metamorphosed. So those inclusions mean that those sedimentary rocks must have been there before the granite came in. So the sedimentary layers are older than the granite. Okay, and so this is a little bizarre to picture because this is underneath the sedimentary rocks, but that doesn't mean it's older. It just means that it came up and intruded. Now, another thing that helps us with this process is that the granite intrudes into the sedimentary layers here and here, which also indicates that the sedimentary rocks were there before the granite came in. So, two more principles, I believe. The next principle is called the principle of lateral continuity. And that principle simply states that sedimentary rock layers are horizontal for great distances. In fact, you can see here, this goes all the way across into the other side of the Grand Canyon, hundreds of kilometers even to the north. Okay, so all sedimentary rock layers are continuous until they reach something that stops the deposition, like the margins of a basin or a lake or a river where sedimentation has stopped. Okay, so that's the principle of lateral continuity. And here's another illustration of that and how it's used. So here is metamorphic and igneous rocks in the mountains. Here are some layers observed in river canyons and on top of mountains. And here is an oil well that's drilled down into these different layers. Okay, so based on the principle of lateral continuity, we can infer that these layers, okay, if they're still horizontal, extend all the way across this region. So this layer, for instance, extends through this canyon all the way to the mountain front, and then this direction to this canyon. So that principle of lateral continuity allows us, or gives us, some sort of support to make these types of inferences. Finally, the principle of faunal succession. So when geologists first started looking at rocks, primarily in the United Kingdom, they noted that sometimes they could predict when rocks would be the same age based on the fossil evidence. So the central question is here, over large distances, how can we correlate age of sedimentary rocks? And one way we do this is through using fossils, or the fauna found within the sedimentary rocks. And here's an example of that. Okay, so here's a stone quarry, a hillside exposure, and a canal excavation. Okay, so this is 3 different localities. So notice in this shale layer we find this sand dollar, okay, this echinoderm. And also over here on the hillside we find a similar rock type with a similar fossil. So based on the principle of faunal succession, based on the principle of lateral continuity, we can say that these 2 layers are of the same age. And here we have shale in the stone quarry, and we have shale on the hillside exposure that have these ammonites. And once again, we can infer that those shales are the same age based on the principle of faunal succession and lateral continuity. So when we finally make this stratigraphic column, we can use data from these 3 areas to make a very thorough picture of the geologic record in this area, starting with this slimy sandstone and ending with this shaly material at the top. So we can combine data from different sites in order to make a strong, or a much more detailed stratigraphic column, which then we can use to do things like interpret relative sea level. So when we put all this together, what was developed was a very detailed geologic timescale. Okay, and the geologic timescale consists of eons, eras, periods, epochs. Okay, so this part of it here wasn't really established until we started getting more absolute ages associated with these rocks. This part of it was established through very careful field work, which was used to correlate sedimentary layers across the globe. Okay, so these names, especially the period names, represent areas like that were characteristic, like the Devonian is Devonshire in England, the Carboniferous because it had lots of carbon, and so forth. So these names are primarily developed around where the typical rocks were found for these periods. So this was a huge endeavor. It involved hundreds of geologists, thousands of observations, and what's cool about it is that the observations which were used to construct this were substantiated later when we got absolute age dates to support the development of the geologic timescale. So here's an example of how this was done in terms of developing the geologic timescale. Okay, so here's a sketch of an outcrop, red sandstone and shale here. Notice that the rocks are tilted, which means that they originally were horizontal, so something happened to tilt them, some tectonic process. And then we have these horizontal layers of sandstone and then this gray limestone and black shale interlayered. And note that we have these different fossils from these different locations. Okay, so what we can do is if we can correlate these fossils that are found within these different layers with areas, different areas, or from different areas, then we can construct or correlate these observations with the geologic timescale. So we know that the ferns are associated with Pennsylvanian type rocks, the ammonites Jurassic, and the clam and snail species are this tertiary or Paleocene and Eocene time. So we're using the fossils which have been correlated with a specific time period to make inferences about the age of these different sedimentary layers. So one of the things we're going to need to do is to practice with these principles, and I'll do a short video later about how to do this. We're going to use these models of geologic processes, and we're going to try to look at these and make some inferences about which rock type is older and which is younger. Well, I can do this one now, right? So looking at this very schematic sketch, a model of layers, a fault, and a new layer. The oldest rock is B, so that would go down here. The next oldest rock is W, and the next oldest rock is E, so it'd be B, W, E. And the principles we'd use for that are what? Well, the main principle would be superposition. Rocks on the bottom are older than rocks on the top. So the next event that happens is Q. Okay, the fault cuts across these layers. Okay, and how do we know that? Which principle? That is the principle of cross-cutting relationships. So far the order would be B, W, E, Q, and then the next layer would be K, and that's also the principle of superposition. Now we know that K is younger than the fault because it covers the fault. Okay, so it's a newer layer. So I challenge you to try this one here, doing the same type of process. More brave and see if you can do this one. These are kind of commonsensical, but are also based on lots of observations and therefore a very valid type of scientific endeavor. So I hope you enjoy this, and take care.